Good afternoon, everybody. My name is Boelo. I'm Scientific Vice President of the European Federation of Chemical Engineering. After being a board member of the Netherlands Process Technologies for 6 years and representing the Netherlands in the General Assembly of the EFCE, I've also served as the Secretary of the EFCE Working Party on Fluid Separations for 6 years. I've now been in the board of the EFCE since January of this year. I'm a chemical engineer by training, and I received my degrees from the University of Groningen in the Netherlands. I built my career in academia, and since 2011, I work at the University of Twente in the east of the Netherlands, where I'm currently a full professor, and my chair is called Sustainable Separation Technology. I'm very happy to introduce this webinar on circularity and sustainability in the light of polymer reaction engineering, a topic that is close to my heart as Sustainable Separation Technology professor. Let me say a few things about the Spotlight Talk series. This is the 5th year that we organize this, and since this year is an even year, we don't have an ECCE, a European Conference on Chemical Engineering, and for that reason, next to the annual spring sessions, we also have this fall series of Spotlight Talks. And last week and this week, in total, 13 of the working parties and sections are participating. That includes sustainability, mixing, electrochemical engineering, high pressure technology, food, loss prevention and safety promotion in the process industries, agglomeration and multi-phase fluid flow, static electricity in industry, education, thermodynamics, transport properties, early career chemical engineers, and this afternoon, polymer reaction engineering. So after today, there are still a few more of these sessions, and you can still register for them on the website of the EFCE. The EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers in Europe. The EFCE's working parties and sections cover all major chemical engineering aspects and are the core of our organization. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, I would like to thank all the people who have worked hard in the working parties, and this afternoon for the working party on polymer reaction engineering, and of course to Martine for her effort in setting up this series. I thank you for your attention, and I wish all the speakers and the attendees a fruitful and successful webinar. I would like to give the word to the chair of the Working Party on Polymer Reaction Engineering, Professor Markus Busch.
Thank you, Boelo. Many thanks for this very nice introduction, and I'm happy to welcome you all here for this webinar. I've seen that we have now close to 60 participants, and I heard about 140 enrollments, so that there may be even a growing number. When starting this webinar this term, it was starting slowly, but then we got very high activity in terms of the speakers, and this was that good that we have already plans for the second webinar that will be focused then more on modeling in polymer reaction engineering, certainly also with the focus on sustainability. Sustainability in polymer reaction engineering is a major topic and is shaping the future, and is also an enabler for the future and future technologies. And this is what we would like to address today. So I welcome you, and I'm very thankful for the speakers that they are presenting here. And I'm handing over the word to Kristina, my secretary, on my right hand. And I would like to make a very last comment. All the visitors, they cannot speak up, but if you have questions when we address the discussion, please use the chat to address your question. We will read it to the community, and as a speaker will answer. So thank you, and enjoy the talks, and I hand over the word to Kristina.
Yeah, thank you very much, and also welcome everybody from my side. So I'm looking forward to the program. I'm really excited for the presentations that we are looking forward to. It's my pleasure to introduce the next speaker. This is Pingwei. He did his PhD at the Zhejiang University in China. He worked at the MIT as a postdoctoral researcher, and he has a strong background in polymer reaction engineering, but also two-dimensional materials and nanotechnology, and also a very impressive record of publications and awards. So he's currently working as professor at the Zhejiang University in Hangzhou, China, and I'm looking forward to your presentation on sustainability-driven polyolefin reaction engineering. So,
thank you, Kristina. Thank you for the kind introduction. So can I share my screen now?
Yes, please.
Thank you. All right. So can you see my slides?
Yes, they are not yet in presentation mode. Perfect. Now it's wonderful.
Noise. Can you see?
Yes, yeah. It's perfect.
Okay, thank you. So I'll start. So good night, good afternoon, everyone. So here in China is night. So today I will share our progress in the sustainability-driven polyolefin reaction engineering. Most of this work are done with my co-workers, Professor Bogan Li and Professor Wenjun Wang, Professor Pingwei Wang, and lots of this work being presented here are done by my students, Yang Kexiao, this girl here, and also this girl, Kan Liu, and Yin Long Chang, and several of my graduate students before. So also I thank the financial support from these departments. And my talk today will be divided into these parts, 5 parts. First, let me have a brief introduction. Okay. So, polyolefin almost accounts more than half of the plastic in the world. So, and the growth of the polyolefin market is also with a high number. You can see from 2022 to 2008 is predicted to be 96% each year. So it's a very huge, increase tendency. And among all different polyolefin products, there is one very special products this was high-end polyolefin products. For example, those synthesized by the metallocene, polyethylene, propylene, and their copolymers. For example, one of very interesting one is the polyolefin elastomers that will be mainly covered by my talk today. These polyolefin copolymers, they are usually synthesized by the copolymerization of ethylene and alpha olefins. So they can have, for example, those unforced part is just a copolymer of this part with a high content of alpha olefins. So they are unforced. And they also have those segments with no content of alpha olefins. So that means they can be crystal and form a physical cross-linking. So in this way, you can have a physical cross-linking to bind these chains together, so then can form a good elastomer. And because of this, they can widely applied in different fields. For example, you can use them as the CO materials for the photovoltaic cell, a very, huge area, increase dramatically. And you can use those automobiles, especially those new energy-based automobiles and medical devices. All because they are processed very simply, they are elastic, and more importantly, they are recyclable. So another big reason is because this POE are believed to be maybe can replace part of the conventional rub that based on the irreversible cross-linking. Everyone know these rubbers are prepared in a very complex process. You need to cut the gel to roll and mix and work lice to form a permanent chemical cross-linking. And most, you need to have lots of energy input during this process. And they are really difficult to reuse and cause lots of pollution. So this is the reason why people work on so much to develop this polyolefin elastomers. And during the last decades, actually in our lab, we did lots of work trying to first we trying to regulate the physical crystallization in the polyolefin elastomers, trying to get a high performance the polyolefin elastomer with a short process. And recently we kind of introduced the dynamic cross-linking into the polyolefin elastomer trying to still have a high performance the polyolefin elastomers, and this can still be processable. And most recently, we think like maybe we can use the polyolefin waste or the new raw materials, and we trying to do the cracking to oligomers, and based on the dynamic cross-linking, we are trying to synthesize those like high performance the polyolefin elastomer with this raw polyolefin waste as raw materials. And all of this work is kind of like we wanted to propose today is use the polymer olefin reaction engineering for more sustainable POE and polyolefin products. So first, I would introduce my work like by using the tandem polymerization to do the chain regulation of these polyolefin elastomers. So like if you consider the chain structure of this like polyolefin elastomers, so the most simple one will be to have a random polymer. You have some segments they can crystallize, and the same segments they are like highly amorphous, and you can form like a POE. And if you tune the structure, you have a block, for example, like multi-block chains, then you can have a higher melt point, and their performance will become better. And in our lab, we think we can also develop a new POE based on this grafting structure. For example, we can graft in the crystal-like chain on the side chain, and we have an elastic backbone. So that in this way, we can also develop like high performance polyolefin elastomers. And this is basically what we wanted to do in our lab. We first use like oligomerization catalyst to do the ethylene oligomerization to form a micromole with high crystallinity, and then we use it for the copolymer with comonomer with oxidine and ethylene, then to have an elastic backbone. In this way, we will develop our cobalt POE, and we use the Fi zeroning catalyst for the oligomerization. We can polymerize the ethylene to form like a high oligomers with the molecular weights around 5,000 kilogram per mole. For example, you can see the molecular weights with the dispersed around like 2.5 to 3.7, and it has a very high main temperature, about like 124 degrees C. And the most important things here, you can see we check with MR, they have like one ends at about like 10% contained. And in this way, we can synthesize micromoles for the further copolymerization with alpha olefins, octane, and ethylene. And in the second part, we do the copolymerization. So for the copolymerization, you can see here we can observe the very brown peak, melting peak of these copolymers. That means we already like copolymerized these micromoles with our alpha olefins, octane, and the octane, and also the ethylene. Here you can see the high main temperature from the crystal part, and the low glass transition temperature from the amorphous part. And in this way, we synthesize the copolymers with a molecular weight larger than 100,000 kilogram per mole. And we also have high copolymerization activity here. If you check the GBC curve, you can see there is still a little bit micromolar residue on this part, and here we have like a huge copolymer. So based on this, we can tune the catalyst, the two concentration of the two different catalysts, and then we can change the amount of the macromolar insert the content of the macro into the backbone. For example, here we still have like some residual macromole inside, but the number of the insert macromolars we can tune from like for each chain have like 1.9 chains, crystal chains to 9.9. So in this way, we can tune the chain structure of our cobalt polyolefin elastomers, and we test the mechanical properties of this kind of CPOE. We find the properties they are better than those like commercial POE, for example, POE 8150 from Dow, and also the olefin block copolymer also from the Dow Chemical Company. You can see here the modulus, elongation, and break. They're good, better than this commercial product. And also the elastic recovery they're kind of comparable to the OBC products. And we further also studied the effect of the residual macromolars on the polymer proteins. What we have done in this work is we mixed some micromolars with the copolymers we synthesized and trying to find the rule when increase the unreacted micromolars inside the system, how it will change the rheology properties of our copolymer system. And we found the unreacted PE residues actually play a role of plastic size during the process, that they can kind of reduce the friction between the polymer chains and facilitate the chain disentanglements of this CPO chain polymers. And we also further studied the chain structure on the how they affect the properties of copolymers. We find like increasing the insert number from 1.9 to 9.9, the planes has a faster reduction and complex similar rheology behavior. For example, if you check the cocoa plots, you can see they can become smaller as the Q increase from 1.9 to 9, the small diameter here you see here. And also if you check the master curve, you can see the like upturn with the increase of the number branch number. So all this like demonstrate like a complex similar rheology behavior. And finally, we found like if we increase the number of the chain on the side chain, we can go to from like a loose cobalt to a density cobalt, and the properties are pretty different. For example, in the loose conformation at this area, the backbone and the branch chain process unperturbed random Gaussian conformation, and the friction between the branch chains is dominant. Once you go to the density cobalt structure, the eta 0 will be increasing with Q, and the dilution effect of the branching chains will be stronger than the friction effect. So the eta 0 will be decreasing with the increasing Q. So we also do some modeling, trying to figure out if we can model in this tandem polymerization process, trying to, for example, if we want to tell in the structure, we should have the modeling for that. And we find that this process is pretty challenging. The reason is because we have 3 monomers and 2 catalysts in this system. If we write the limit reaction out, we find we have almost like 31 parameters for the calculation. That means our computation time will be exceeded 2,000 hours, and it also have a risk of overfitting. So we developed a method using like what we have done is like trying to use the organization method to reduce the number of parameters. For problems with a long computation time, we use the machine learning instead of the ODE solve, which is the most time consuming because the ODE solve consume lots of time. What we have done use the machine learning to do that. But the thing is like machine learning requires lots of amount of data to train. So we use the ODE solve to generate like maps of millions of set of inputs, and the kinetic parameters that are based much on the experimental value will be go to the adaptive optimization loop. And by doing this, we can use the machine learning data for the product design. And this is what we have done for the, you can see if you use the machine learning lighted LGB model, we can significantly reduce the time for the calculation. And our results are good fit with the experiment. Here is the flow rate of the ethylene, and this is the calculated one, and this is the cumulated composition of the oxidane inside the chain. You can see here we can have a better match of the experiment, and calculation results are also included the molecular weights and their dispersity. And here is the weight of the residual micromonomers, and this is the insertion number of the branching chain. So finally, with this model-guided CPE synthesis, we can reduce the residual content of PE micromolars and also increasing the micromolar insertion. By doing this, we can control the CPO chain structure to get a higher performance. And the second part, I would like to introduce our recent work. on trying to further increase the mechanical performance of these POE products by introducing the dynamic covalent chemistry inside. Because we know like crystallization is kind of like a steel weakening force. Their intermolecular force is based on the physical correction. Crystallization is a one-to-one force. It's still pretty weak. But if you want to increase this like kind of like interaction, you can go to the covalent bonds. But in the traditional rubber, this kind of like a covalent bonds, because they are permanent cross-linking. So that means you cannot reprocess the product after they are cross-linked. But in this year, we found there is a new development in the chemistry field. They call it dynamic covalent chemistry. For example, the diallyl, like disulfur radial, and also like a bromine ester. This kind of chemistry, they are dynamic. So if you heat it up, it can have an exchange between, for example, with the neighborhood groups. In this way, you can still have a reversible cross-linking, and the strength will be much higher than the physical crystallization. So based on this simple idea, we are trying to introduce this kind of like a dynamic cross-linking into a polyolefin elastomer network. And during this process, there is no catalyst which is required. And another good thing is like because this of like bromine ester group, they are pretty like have no activation energy for the bond change. That means they are not stable. But the thing is, if we have crystal in the POE, so that means maybe in the otherwise we can help to increase the activation energy of this kind of bond. And another thing is this kind of like group, they are highly sensitive to water. But the good thing is the polyolefin elastomers, they are pretty hydrophobic. And another way, it can protect this group when they are embedded into the network. So based on this simple idea, we proposed a new chemical route. For example, we introduced some like a pendant winding groups onto the backbone, and we use the click chemistry, introduce some diol groups, and these diol groups can be cross-linked by the bromine ester. You can see here from this kind of cross-linked structure, and we can tune the molecular weight and their dispersity and also the diol content. By doing this, we are kind of form a network. This kind of network we characterize with our spectroscopy, and you can see the cross-linked amount of the diol amount. We can increase from 0.6 to 1.8% more, and the residual one, we still have some residual diol do not react. The percent is about like 0.2 to 0.3. And we also characterize the nominal thickness, their crystallization, structure of these like polymers. And you can see after introducing the cross-linked structure, their laminar thickness become a little bit smaller from like 2.97 nanometer to 291, just a little bit of change, not too much. But in this way, we can kind of like a synergy between the chemical cross-linking and also the physical crystallization. So in this way, we have kind of like developed like a higher performance polyolefin elastomer. So you can see here, they have higher mechanical performance. Their fracture strength can be increased by 26 to 137%. And their elastic recovery ratio after cross-linking also can be increased from 98% to 89 to 94. And the most important things, they are also have like improved heat resistance. For example, once the temperature go to like more than 150, this kind of like a cross-linked polymer, they still have like a storage modulus around like 1.2 to 2.9 megapascal, and you can see here planar here. And if you're doing the stretching at a high temperature, 120 degrees C, they still show certain strengths 5 times to those like without cross-linking. And the interesting is here, even like they have been chemical cross-linked, they can be still reprocessed. For example, we did 3 reprocessing of these cross-linked BPOEs, and they still have showing good performance. You can see here, this is like first, second, and the third recycled. Their tensor curves still almost can repeat each other. And this performance are still superior to engage like a POE 58150 of Dow Chemical. And we also studied the characteristic relaxation of this kind of like polymers. If you heat up, you can have more body. These bonds will favor change because like these kind of groups at a high temperature, they can kind of like exchange with the neighborhood. And in this way, they have like a relaxation. And this kind of relaxation temperature is dependent on the temperature. High temperature, the short time for the relaxation. And in this way, we can calculate the activation energy of the relaxation process. And here we find with more diol groups remaining and the activation energy becomes low. You can see here from BPO1 to 3 and the low of the activation energy because more diol groups remaining. And finally, we find if we can, maybe we can still further simplify the process. For example, if we have some backbone, they're elastic, have like some pendant groups here, for example, the winding groups, maybe we can just use the micromonomers. They can be physically crystal, and we can combine them together with cross-linker with dynamic chemistry bond here connect with the cell group. The cell can react with the winding groups here, and this dynamic chemistry bond, they can exchange it at high temperature. So in this way, we can develop a more complex TPOE products or polyolefin elastomer products. And we have grafted structure. They can be increased from like 1.3 seconds to 1%. And the cross-linked amount can reduce from 57 to 30. So there is a competition between the cross-linking and the grafting. By doing this, we can tune the crystallization and the cross-linking at the same time. And you can see here we can have no glass transition temperature and also high melting point. And in this way, we can develop a much higher performance polyolefin elastomer here. You can here we can have this performance. They exceed almost all the commercial product and the product we just seen in the previous slides. And they can also be reprocessed. For example, here we can still reprocess for several times, and they are even can be transparent after recycling. So this kind of like performance, they are all based on the synergy between the crystallization and also the dynamic chemical cross-linking. So because you can see here, if you heat it up, there is a melting of the crystallization part, and also the dynamic chain will be they'll be exchanged, and it's kind of like have a relaxing time. In this way, you can do the reprocessing, and we also doing the calculation of this activation energy. And here you can see here the activation energy is higher than the previous one we showed in the a few slides ago. The reason is we introduced this kind of like a crystallization part. They are kind of like limited the relaxation during the high temperature. Okay, so I think I already like introduced the dynamic chemistry cross-linking. So let's think about another thing. Maybe we can not just start from the olefin monomers to the polymer. Maybe we can use those like polyolefin wasters. For example, can we crack it or maybe like fragmented fragment doing the oxidative cracking and make them become like oligomers? Maybe we can use the way how developed, maybe combine them together with the dynamic cross-linking. So like right now, like the plastic waste is becoming a huge problem for society. So if you compare the different methods for the recycling, the chemical recycling become more important because they can kind of like realize the resource optimization, not just the energy. You can also utilize the carbon materials from that and reduce the carbon emission. So based on this idea, we think maybe if we consider like a polyolefin wasters, we have different way to do the chemical recycling. For example, you can do the pyrolysis, you can do the catalytic cracking, and also you can do the oxidative cracking. But all these kind of methods, there is a very big shortcoming is the products are pretty complex. You will spend lots of cost for the separation to get the chemicals that are useful. So recently we propose maybe we can, for example, just like decompose or maybe like cracking these polyolefin wasters into, for example, go to the oligomers. And these oligomers with, for example, molecule maybe like 1,000, like less than 10,000 kilogram. You can, for example, maybe you can directly use the modifier or competitors, or maybe use a bonder. Another thing we can think is like maybe we can do the chain extension of these oligomers to form kind of like polyolefin-like materials. For example, this like blue dots or yellow dots here, maybe they are just like ester bonds or amide bonds. These kind of bonds, they are easy to hydrolysis. So in this way, maybe we can do a recycling of this kind of like polyolefin-like materials. And based on this idea, we kind of propose maybe we can do the oxidative cracking of polyethylene to form kind of like oligomers with end functionality. For example, carbon oxy groups here. We can also, for example, oxidize those like rubber materials, for example, like for cis polybutadiene to form like epoxidized cis PB. And these kind of two raw materials, oligomers, if we can use the dynamic cross-linking to cross-link them together, maybe we can also achieve like a high performance polyolefin elastomer. And we did this, and we foster do the oxidation, and you see here we oxidize this high density polyolefin with a high molecular weight to the low molecular weight around like 1.5 kDa, and the dispersity is around 3. You can check here we have about like 35 to 40% of carbon oxy groups on the end, and use this of raw materials. We then cross-linked with the epoxidized cis polybutadiene, and we characterize the structure, and we find like once we form this kind of like polyolefin elastomer, we still can observe the low glass transition temperature, almost like minus 90 degrees C, and we can also have a high melt point here around 100 degrees C. So in this way, we kind of also built a new dynamic cross-linked elastomer. And we checked their mechanical properties. We find that the fracture strength can go to like 16.4 megapascal, and their elongation can go to like 600%. The elastic recovery can approach to 80%. And if we compare this performance with those like SBS, those like traditional C elastomer in the literature, they are better performance than reported ones. So we think in this way, we can achieve like a high performance elastomer just using the waste materials or the raw materials. And they also have like a good heat resistance. For example, here you can see like they still have a storage arguments around like 1.4 megapascal, even at the high temperature of 180 degrees C. And I think like almost done here. So also we can do some like study here about the active energy, and here the activation energy is much higher than those like we have been showed in the few slides before. Because the reason is because this network become more complex, and the content of this like functionality and it's less than what we have achieved in the previous part. But anyway, they can still be processed. And in this way, we can achieve a recyclable elastomer based on the dynamic cross-linking with the waste polyolefin materials. So without this, I think I will stop here. So first, we construct a tandem catalyst system for the CPO synthesis. And in this part of work, what we made it done is try to introduce the crystal chain to tune the crystal structure in the POE system to get a higher performance. And we also, in the second part, we introduced boronic ester cross-linking, which is dynamic. So we can have a high performance polyolefin elastable. They can still be reprocessable. And finally, we kind of like renew all the material, raw materials we used for constructing this high performance polyolefin elastable, that we use the polyolefin waste and oxidize them, cracking them into oligomers, and then use the dynamic cross-linking to bind them together to form like a high performance polyolefin elastomers. And without this, and thank you, and thank you for the listening, and I'm happy to answer any questions. Thank you.
Thank you very much for this very nice presentation, ranging so many different but also linked properties. So a nice overview, thanks. So all the participants are again welcome to type questions into the Q&A now. I will keep an eye on them. Maybe while people are typing, I can start with 2 questions I have myself. Could you maybe again elaborate a bit on how you mimicked the recycling process for your materials? So you demonstrated the properties of the materials after several recycling steps or repeats,
You mean
if I understood correctly. And
you mean the
I
last?
was curious, how did you do that? Sorry?
Okay. So maybe I can ask your first question first. Okay. So you mean like these slides here?
I cannot see your slides anymore. Can you maybe show them again? Unfortunately, I missed to write down
So wait for a
the
moment.
slide number. Can you share your screen again?
This
Yes.
one?
Just a second. Screen is at the moment. Yeah, there it is.
This one here?
No. I think it was a bit before that.
Here?
No, it was. Well, I do have a question to this as well, but it was the section before this, I think, where you talked about the yeah, yeah, I think.
So maybe can you repeat your question? Maybe we do not need the slides.
Yes. So I was wondering, how did you mimic the recycling of your materials? So, I mean, you did not like, did you extrude them or did you just cut them and hot press them? Did you
Oh, I
stabilize
see, I see.
them somehow?
So,
So how did
oh, I
you
see, I see, I
proceed
see.
with that?
I see. So for the experimental demonstration in our paper, we just say get these materials combined and then cut it to like very
Mhm.
small pieces, and then we do the hard processing. So this is
Okay.
one way we show for the reprocessing. And for this part of work, so actually we did some like extrusion reprocessing.
Okay. Okay. So there's a difference. Okay. Thanks a lot. So my second question was actually linked to, so this is a perfect slide to ask the question, the oxidative cracking. I think on one slide you also had mentioned that you do it at 110 degrees C, yes, and with oxygen. How long does that take, this
So
process?
for the reaction here, it takes about like 6 hour, 6 hour.
Okay, so you're working in the melt, I assume, or close to the melt, and then.
Yes. So this one we for this one here we use a little bit of solvent trying to
Okay.
dissolve, but right now we can do this in aqueous solution in water with a different catalysis. So right now we developed a new inorganic oxide inorganic catalyst that can do the oxidative cracking of high density polyethylene in water for like 2 or 3 hours, and we can still get like oligomers, like get salt like with a molecular weight around like 2 or 3 thousand kilogram per mole. But for
Okay.
this work here, we do it in solution. We use like kind of like organic solvent to try to dissolve it first.
Okay, and then use the high temperature for the oxidation and for the better solubility, I assume also.
Yes, yes,
Because
yes,
it's quite close
exactly.
also then to the melting temperature. Okay. Thank you very much.
Thank you.
So
yeah. I may have another question for the dynamic cross-linking. So I understand this is the academic treatment, how you do it. You have an idea about like you would like to implement a mechanism and then you demonstrate it. So you synthesize it, you cut it into pieces and then you reconfigure it and you're happy like having 5 to 6 cycles and to demonstrate that this is longer duration, but it goes a little bit in the similar direction, like the question of Hannah Mangold, Hannah Mangold. So a little bit simple to say is later on in application, if you recycle it from the customer, how do you count or how does it perform in cycles? Because over several cycles, I'm pretty much sure that it will deplete in quality because of other chemistries that happens, and then you get back mixed materials. So materials that has maybe twice released, materials that has been 10 times released, and it's all cross mixed. So did you ever try how this material behaves when you mix it in terms of materials that have been aged to different extent, and where is then the quality of the material at the end? So are you already as far as that, or is it at the moment just having the clear starting point and then try to do the simulating the recycle ratios?
Thank you. So thank you, Marcus. It's really like very challenging, but a very good question. So I would say like for the research, so for the academic research, so trying to kind of like demonstrate the concept. So we just use what I have mentioned, like use the materials, you cut it and just like hard process it, trying to reprocess it, yeah, because it's kind of like for students, for them too easy to carry on conduct the experiment. But I mean, what you mentioned, I guess, is for reality. I mean, the materials after using they will be aged, and I mean, their chain maybe like you will break, and if you have we ever tried that? I would say no, not yet. But I think if we want to put this method into the practical, this is one thing we certainly need to consider. So also like this is one thing like what we have right now we are just doing in we're doing in our lab is trying to collect those like waste polyolefins from the from from the different like connect those like waste polyolefins and trying to use our method. If we see we can still get some like polyolefin elastomers with a performance, for example, still comparable to those like pre-star original materials. So this is one thing we have right now trying to conduct. But I mean, what do you suggest? Like doing some aging and then do the reprocessing definitely was to try. And I think this is a very, very good direction to go. And anyways, I think like this is, I mean, I would really ask the students to do that. But I mean, the students maybe more, they can be more practical for their research.
Yeah, I do understand that. Absolutely. But it was just for curiosity, because this would be the next step, getting it closer to a demonstrator for application. And I would really be curious about that. But that's all fine. No. Just knowing about where the state of the art is at the moment. Anytime I'm fascinated that this functions already to this extent. Good.
Yeah,
Thank you.
Thank you for the question. Thanks.
All right.
So
I think we have no more questions from the audience. Then we can continue with the next speaker.
All right. Thank you.
Okay. So I think Professor Boelo, you appeared. Are you there?
Yes, I'm here.
Okay,
great.
Perfect. So maybe we can have your presentation next, if you're ready.
No, I was mostly for questions, not for presentation.
Oh, okay.
Okay.
And concerning this presentation now that was made now, I think that the difficult thing would be to control the hard and the soft domains, because we in polyurethanes, for instance, we have a very accurate control and we can control the hardness of the elastomer. But in this case, it will not be easy to control the hard and the soft domains. I think this will be more difficult in polyethylene and polypropylene. And by the way, the designation PO is normally not used for polyolefins. We use it for propylene oxides and not for polyolefins. But okay, it is a question of nomenclature.
Good. Okay, dann machen wir mal
Okay.
weiter.
Then I think then in this case, then we can continue with Alexandr Zubov and his presentation. I can see he's turning on the camera. Perfect. So Alexandr Zubov, or Sasha, obtained his PhD from the UCT in Prague. Then he did a postdoc in Denmark, returned to Prague, becoming first assistant professor, and then quite recently was also promoted to associate professor. And Alexandr has a very strong background in mathematical modeling for reaction engineering, and he worked quite a lot already on conventional polymers, multi-scale modeling, but also on bio-based and or biodegradable polymers more recently. So it's a pleasure to have you join the session and to talk a little bit about modeling in the context of sustainability. So the floor is yours. We are looking forward to your presentation, Sasha.
Thank you very much, Kristina, for your kind introduction. Can you please hear me and see the slides that I'm sharing?
Yes.
It's all fine.
Great, thank you.
Perfectly.
So as you can see, this in this presentation, it's I will be presenting more collaborative effort with colleagues from Belgium, from University of Hasselt and KU Leuven, because all the mathematical models, in the end, they need to rely on experimental data. So that's where our colleagues from Belgium come into the game. I would like to start with explaining what I mean, or what we mean by biodegradable polymers. So my presentation will be focused on two of the most prominent, or maybe most popular, one of the most popular, definitely, biodegradable polymers of the present days, which are polylactic acid or polylactide and polycaprolactone. Both of them, they found their their place on the market, like in 3D printing, scaffolds in tissue engineering, etc. But still, we can't definitely speak about replacing all the traditional commodity plastics, like for instance polyolefins, with these polymers. And one of the reasons is of course the price for which they are produced and their technical properties. So as I have here noted, they are both fully compostable, and moreover, PLA can be obtained purely from renewable biofeedstock. They share many similar properties, mainly with respect to their industrial production. So the process is catalytic ring opening polymerization. Similar catalyst is used, similar reaction conditions, and also the kinetic scheme of the polymerization that is usually used to describe the process is usually more or less similar for both of these polymers. So what we do, or what are our interests, which I would like to highlight here in the presentation, is modeling of industrial polymerization, mainly for the sake of optimization and control of the process. We are interested in polymer melt rheology, which is important in processing of the product. And then I will slightly mention the problems of depolymerization, which we see as a straightforward and elegant way of recycling the polymer, and also how to enhance speed of computationally demanding models. This is basically what I just mentioned is the structure of my presentation. So first I will present the modeling framework, which we call multiscale, that we use to predict basically properties of the polymer based on the reaction conditions in the polymerization reactor. I will show how this framework can be used to model production of PLA and polycaprolactone. And then I will briefly mention the two topics that are work in progress, the polymerization and surrogate modeling or meta modeling for Monte Carlo models. So let's start with the multi-scale modeling framework. The whole model that we build here is based on three important parts. The first one we call macro scale or macroscopic or process model. So this is basically a set of ordinary differential equations that look at the reactor as a big vessel, ideally mixed, where and using the model we can actually predict the evolution of concentrations of the species that are present in the reactor in time, and also some average properties of the polymer molecular weight distributions, which are number and weight average molecular weight and their ratio polydispersity index time. Some of the informations that are produced in this model are then sent to the second part, which we call microscopic or Monte Carlo simulation, during which we basically replicate the simulation done in the macro scale, but we look at each chain separately, individually, and therefore this simulation is much more computationally demanding, but it allows us to get detailed information about the molecular chain structure. So using Monte Carlo simulation, we can predict the full molecular weight distribution of the polymer. And then the information, this actually the structure of the chains is then sent to the publicly available model, which is called BOB, developed at University of Leeds, which we use to predict the rheological properties, viscoelastic properties of the polymer melt, which is mainly the G prime and G double prime moduli as two parts of the viscoelastic behavior. If we focus on the macro scale reactor, basically we didn't have to do that much here. We just took a great paper that was produced at ETH Zurich by Yu and his co-workers, who actually carried out several experiments, proposed a kinetic model and validated this kinetic model using the experimental data. So the only thing we did here is that we implemented the whole model in Fortran language, including all the kinetic rates constants that were published in this paper. And if you look at the proposed kinetic scheme, you may notice that most of the reactions are reversible, which I will address later on in my presentation. And there are some specific and important reactions which usually cannot be neglected, which is this intermolecular transesterification that leads to the broadening of molecular weight distribution at high conversions, and also random chain scission of polymer chains, which leads to the decrease of molecular weights at higher temperatures. As I said already, the Monte Carlo model is taking some data from the macroscopic model, from the process model of the reaction. It is based on the classical Monte Carlo algorithm that was first proposed by Daniel Gillespie in 1970s. And basically using we call it hybrid because it cooperates with the macroscale model in a way that it estimates reaction rates based on the concentrations pre-calculated by the macroscopic model, and based on the reaction rates, it estimates the probabilities of individual reaction steps, and using these probabilities and random number generator, we can in each step of the algorithm we can generate or we can select one specific reaction step that will happen in this particular iteration. So, for instance, at the beginning of the polymerization reaction, there is a high probability of propagation. So most of the time the propagation step is selected, while towards the later stages of the polymerization, we have a higher probability of transesterification or chain scission reactions. So this way, we actually build each of the polymer chains step by step, and that allows us to get the detailed information about their architecture, which can be later on translated into molecular weight distribution directly comparable to experimental data such as size exclusion chromatography or gel permeation chromatography curves. The last model, which I already mentioned, is called BOB, which means branch on branch. It's publicly available. It's based on tube theory of entangled polymer chain repetition, which I always imagine as a bowl of spaghetti, as you can see in the picture. It wouldn't be possible for me to tell actually more about the theory that is behind this model, because I would have to have a PhD from a different field probably. But as far as I know, especially with respect to general branch-on-branch architecture of branch polymers, this is the state of the art in the nonlinear rheology, and its first version was published already almost 20 years ago. And as one of the most important inputs here is the molecular architecture of the polymer chains, as I already said, that we take from the Monte Carlo model. Then there are some physical properties like polymer mass density, temperature, etc. And then there are two uncertain parameters which need to be estimated, and that's the chain entanglement time and average molecular weight between two entanglement points of the chains. So how can we validate the model or the whole framework if we have it built like this? First, we need experimental data on polymerization and also to have the kinetic parameters of the polymerization estimated. Then we need to have experimental data on rheology of the produced polymers, hopefully with different molecular structure. And then what we do is basically we modify the input reaction conditions in the macro scale model, and we virtually generate polymer samples that are hopefully equal or similar to that have the similar or equal. Sorry, not that they cannot have directly equal, but at least similar as much as possible, similar molecular structure as the real samples. And finally, so in the step 3 we compare the information about molecular weight distributions, and in the last step we compare the information about rheology, and at the same time we estimate the uncertain parameters, chain entanglement time and average molecular weight between two entanglement points. For the PLA, we didn't have actually any experimental data from any collaboration or generated by ourselves. So the situation regarding the experimental data on polymerization itself was easy. As I already said, we took everything from the paper by you and co-workers from 2011. And the rheological characterization, we had to found another data in the paper by Cooper, White and colleagues from 1999, who actually took 3 industrial samples of PLA with different molecular weight distributions and characterized their rheological properties of their melts. So this we did purely on the literature data. And with respect to polycaprolactone, we managed to get a cooperation recently with our colleagues from Belgium, as I said already. So at the university, or Hasselt University, our colleagues carried out experiments or produced basically carried out polymerization experiments from which we basically need average polymer molecular weights MN and MW, number and weight average, and conversion of monomer measured in time, hopefully at different temperatures and concentrations of co-catalyst, which is sometimes also called initiator by chemists. And the rheology then, they sent these samples a few kilometers away to the city of Leuven, where our colleagues from different research groups measured the rheology, and we have just this very fresh data. And the rheology measurement is usually called frequency sweep characteristics. which means a dependency of elastic and viscose modulus G prime G double prime on the changing frequency of the oscillation of the sample during the rheological measurement. So for the PLA, you can see that on the left side you can see the so-called complex viscosity, which is basically how to say it's a property or variable, or not, rather property that is composed, like describing viscoelastic behavior in one number. So it is combining the information about both moduli G prime and G double prime, and at the same time the frequency of the oscillations. On the right hand side, you can see the decomposition of this complex viscosity into the viscose and elastic parts for 3 different samples, which names of which start with letter L here, and the points represent the experimental data from the paper from 1999, and the points represent the model predictions. So with this, actually, we also had to estimate this tau E and ME parameters, as I mentioned already. And since the average molecular weight between chain entanglements was actually quite close to the data or the values that we found in literature for PLA, and the agreement between experimental data and model is decent, here we considered the modeling framework to be validated by experimental data. Regarding the PCL or polycaprolactone, the work is still in progress. Here we have example of 3 experiments that were done at Hasselt University in the research group of Professor Pittet, where in each of the experiments, the conversion of monomer and number and weight average molecular weights are measured. So you see experiments carried out at 3 different temperatures, 70, 80, and 90 degrees. You see from the conversion profiles that normally, as we expect, the dynamics or the rate of the polymerization increases with increasing temperature. And the excellent, at least in the conversion profiles, is excellent. The agreement between predictions and experimental data is excellent, at least in the conversion profiles. It doesn't look that excellent when we look at the molecular weights, but there is still work going on this, and we're thinking about expanding the polymerization scheme a little bit. But overall, even the molecular weight predictions, they look, in our opinion, definitely better than what we have seen so far in the literature regarding the kinetic modeling of polycaprolactone. So not that bad, hopefully. And here I'm just showing for these 3 samples produced by these 3 reactions, 3 experiments. I'm just showing that we also have experimental data on the rheology, but these are very fresh, and so the curves here that you see, they do not represent model predictions. They are just connecting the experimental data, the points. So here we are still waiting for the modeling part to be finished. Now I would like to move to the second and shorter topic of the presentation, because since we had this Monte Carlo model developed, we were thinking about how we can apply it further. So as I already mentioned, in this ring opening polymerizations, most elementary reactions are reversible. If we take a look at the propagation step, we have active chain of length n that reacts with monomer molecule, and since monomer of PLA is lactite, which is a dimer of lactic acid, we have, after the propagation step is over, we have the monomer molecule consumed, and the chain is propagated by two lactic acid units, lactoyl units, basically. If we write down the equilibrium constant of this reaction and assume that the concentration of the chains, of the active chains, actually doesn't depend on their chain length, we get this classical formula that the equilibrium constant of this reaction is actually inversely proportional to the so-called monomer equilibrium concentration. what does it mean? In equilibrium, as we know from this famous thermodynamic formula, Gibbs energy of the reaction is 0. Therefore, we can actually calculate the so-called monomer sealing temperature because enthalpy of the polymerization as well as entropy of the polymerization, they are both negative numbers. So theoretically, for each of the propagation steps, for each monomer, we have a sealing temperature that represents the temperature in which the rate of the forward and backward reaction is the same. So we cannot polymerize anymore. And the sealing temperature is related to the concentration of monomer. And the monomer concentration depends not only on the temperature following this Dainton-Ivan equation, but also since it is concentration, molar concentration, it depends on the solvent that is used. And that is basically the most important idea of this work, which doesn't come from our head. But for most of the monomers, the sealing temperature is typically relatively high. So for instance, for lactite in toluene, the sealing temperature is 600 or more than 600 degrees Celsius. So in order to depolymerize, we would have to really heat up the sample very, very much, which is not really efficient. But in this paper by Cederholm and co-workers 4 years ago, they demonstrated that if they use different solvents than traditional toluene for lactite, they can actually decrease the sealing temperature down to 120 degrees Celsius. And so we were thinking, okay, that's a great idea. Let's try to model this. And of course, we can use the kinetic Monte Carlo model that we already have and build upon that. But also, if we want to include the interactions between polymer, monomer, and the solvent that is used, we will anyway have to use some thermodynamic description of this system. So we can start with Flory Huggins, but that is still rather in the field of ideas than reality. In the paper that I just talked about, they carried out lactite polymerization in different solvents at different temperatures. So for instance, here in the table, you see solvent DMF, which is dimethyl form amide, if I'm not mistaken, and GVL is gamma valerolactone. And you see that with increasing temperature, they are getting closer and closer to the sealing temperature, and their equilibrium conversion is actually getting smaller and smaller. That is basically translated the monomer equilibrium concentration. So this Dainton equation actually can be linearized, and these two sets of data for two different solvents can be put into graph, and using linearization, you can very easily, or linear regression of this linearized data, you can easily estimate the entropy and enthalpy of the polymerization as well as the sealing temperature. And you see that these different solvents lead to really dramatically decreased sealing temperatures of 120 and 140 degrees Celsius, which is something that might be really used, we hope, industrially in reality. So we are able now to process this data to estimate these properties of the polymerization, which we can then use as an input parameters to our Monte Carlo models. And here in this rotating plot, you see one example of simulation of basically how the evolution of molecular weight distribution is changing over time when you depolymerize. And the same is translated here in the right part of the graph. There is a number of lactite molecules, which is the monomer, is increasing over time, while the number of chains, of polymer chains, is decreasing. And here is the information about average number and weight, average molecular weight of the polymer during the depolymerization. And the last part, very quickly, basically is the metamodeling of polymerization, and metamodeling sounds like a magic word, but by metamodel we mean nothing else than model of a model. That means that if we have models, mathematical models that are computationally very expensive, so it takes really lots of time to produce one output of the model, we can actually pre-calculate a few points in the parametric space depending on the set of input parameters, and then use some smart and good enough statistical models to basically cover these predicted data and make a statistical model on top of them that will allow fast and quick interpolation. There are many different metamodels or metamodeling techniques that are reported in literature. Here, of course, since everybody is working with artificial intelligence today, we had to try ourselves. So we built artificial neural network with an idea to replace demanding kinetic Monte Carlo simulation of polymerization. Although so far this model has not been built upon the Monte Carlo polymerization data, and I will explain why. The idea is that we have three input parameters of the model, of the kinetic model of PLA production. That is the temperature of the reaction, concentration of catalyst, and concentration of co-catalyst. We basically generate a lower and upper boundary for each of these parameter and create a three-dimensional input parameter space in which we sample many points, and in each of these parametric combination, in each of these points, we basically run our model. Here, because the number of points was really high, we didn't run the full Monte Carlo simulation, but we just run the macro scale, the macroscopic process model, just to get the number and weight average molecular weight, as well as conversion of the monomer, which is denoted as X here. So sampling of the input parametric space can be done also using different techniques. Here we use the Latin hypercube sampling, which is one of the most popular techniques. Then we run, for each of these parametric points, we run the simulation and get the outputs. So three of these characteristics. And then we take this artificial neural network and train and validate it on using this black box input-output relationships. And as you can see from this animation, with the higher number of training epochs, the artificial neural network is getting better and better. So in the end, the relative error, or the difference between the originally predicted values and the statistically correlated ones, the error is smaller than 3%. And of course, the response of artificial neural network, even considering the original macro scale model to be relatively fast, getting response in less than 2 seconds, the artificial neural network actually, the response, if it is trained well, the response is not only accurate, but it's also immediate. So in the end, the trained neural network is actually 5,000 times faster than the original macro scale model. Of course, the idea is for the macro scale model, we don't need the metamodel that much, but it would be definitely needed in the case of Monte Carlo, where actually we are not interested only in the averaged polymer properties, but we also would like to know the full molecular weight distribution of the product. So the next step of this work is actually to start working or to train the network not only to predict scalar values, but actually to predict the whole distribution curves. So that is actually work in progress. So to conclude my presentation, I can say that we built a multi-scale modeling framework which relates the polymerization reactor model, polymer microstructure evolution, and rheological properties. And we validated using experimental data on linear polymerization of lactide and caprolactone. We believe that based on the results that we get, the production of polycaprolactone by catalytic ring opening polymerization can be modeled using the same kinetic or very similar kinetic scheme as is the production of PLA. We try already to build the model computationally efficient as much as possible. That means on standard average desktop PC, you get from the input reaction conditions to the rheology of polymer melt, you get in a few seconds, but still for more complex samples and longer simulations, the development of faster models is necessary, for which we are trying to use the artificial neural network. And we are also interested in modeling the polymerization of these biodegradable polymers, which again can be done using extension of the already developed scheme. So that's all from my side for now, and thank you very much for your attention.
Thank you very much for your presentation, Sasha. Very interesting overview also of different aspects. Again, for all the people listening, feel free now to use the Q&A to type questions. Oh, yes, Professor Boelo, you have a question already.
Yes.
Please.
Well, Alexandr, very interesting presentation and very useful for some applications. But you know that from the industrial point of view, when we produce PLA, the quality of the PLA and the type of PLA depends a lot on the purity of the lactide. And different types of impurities give rise to completely different PLAs. And it's the explanations are not yet in place. And my question is, how do you intend to input that in your model? Because until we understand the mechanisms for these different behaviors of the final PA, it will be difficult to input in your model.
Yeah, thanks for the question. I absolutely agree with you, and I'm afraid that there are phenomena which are extremely difficult, if not impossible, to be actually included in the model. So this work is, is basically like the first steps that we can take. Okay, so let's do some kinetic modeling. We believe to get some progress later on with more complex stuff like copolymerization, etc. But the question of impurities, maybe sometimes they can be introduced into the model like empirically, but that is not then very much useful. The only thing I can say is it reminds me when I was many years ago working on the model of styrene butadiene rubber production for the Czech producer. This synthetic rubber is not produced actually anymore here, which is pretty sad. And I hope it's not because of my modeling involvement there. But I remember I developed some model which was more or less consistent with the data from the production. And then after some time, I went to the production to see the site actually, which was very interesting. And the main technologist there looked at me and said, you have your models and your nice predictions, but how can you introduce into your model that 1 week ago we got the same emulsifier, chemically the same component, the same molecule from a different provider, and the polymerization is running 7% slower. How will you include this? And the response is actually yes. That's something we cannot actually include. How can we? With the state of the art, what can we do here, right? So I'm afraid that there'll always be something we cannot reflect in the models. But that's of course very relevant question.
Thank you very much.
I thank you.
Okay. So
Maybe a comment on that also from my side. What Sasha said is, what you described is often the effect of byproducts, and it will be also some challenge. Simulation guys like us will face when monomers come from different resources. So when we change from fossil resources to bio-based resources, we had some tests in that direction. And of course, you have to readjust the process. However, and this would be the counter argument, the models help to learn where to move. So we are not directly hitting the spot. Of course, I will never bet my home on that. But what the models can do is helping moving into the right direction and being quicker with adjustment of processes. And step by step, we learn for sure what byproducts are there and how to include these effects. But that's a long-term progress or process. And this is what we have to walk on the long distance. But if we do that, I'm pretty convinced that this will help. But it is not just a magic thing like now we do it, but step by step we move forward. If we don't move, we do not learn. But if we move, we will learn.
Thank you. That's very nice and positive outlook.
Maybe I also have a question for you, Sasha. Maybe you can show slide 18 again. I think it was rather at the end. Now I took care to write down the slide number as well.
So this one?
Yes, yes. So, I mean, you had the nice number there that it is your trained ANN is now 5,000 times faster. So I assume that the idea is now to make use of this model in optimization somehow, right? Or so do you have something specific already in mind?
Well, so the inspiration for this comes from the previous work that I've done in collaboration with BASF and other European universities, where we were actually working on emulsion copolymerization, and the idea was there to build a model-based predictive control system of the semi-batch reactor in the pilot plant. That means basically control and optimization of the reaction process in real time. That's something that's very interesting to me. And we in that project we managed to build the model that looked not exactly, but the structure of the model was basically following the structure of this macroscopic model. So it was just fast integration of ordinary differential equations. And in that project, we managed to get the model response in, I think, less than 1 second, which was enough for the control system to use it. So it was actually successful. But the idea here would be rather, of course, here we demonstrate that we can easily train the artificial neural network on the average molecular weight. But I would like to actually see the model that would be validated by experimental data and would get the information about the full molecular weight distribution in a less than second. So that's the idea here, and that would be then called soft sensor, like a sensor that is not physically present in the reactor, but is something that, based on the information measured in the reaction, can tell you what is probably the most probable molecular weight distribution of the polymer right now in the reaction mixture.
Mm-hmm. Okay. Thank you very much.
I thank you for the question.
All right, so I can see that we also have no more questions from the audience. So I think, Sasha, with this, thank you very much for your presentation and also for answering our questions. And then we can continue and move on to the last speaker of today's session, Ugur Agkün. He received his PhD in process engineering from the Technical University of Munich and has meanwhile many years of experience in industry, many of which he spent at LyondellBasell, working in the field of polymers. And currently he's the Director of Application Development and Technical Service, working or stationed in Frankfurt. And yeah, I'm looking forward to his presentation, where I think he will talk about technologies and products for sustainable polyolefin solutions with a broad range of applications. So we already heard a bit about polyolefins today, so I'm very much looking forward also to your industry perspective. Thank you very much for being here and presenting today.
Yeah, thank you very much, Kristina, for your kind introduction and also for the opportunity in this forum to talk about LyondellBasell and our approaches, how to solve the challenges for our future, right? Not only for our company. I think it's a topic of the society in the whole. And society means, as we heard here already in the presentations before, what it means. There are a lot of aspects like production engineering, process engineering, scientific approaches. And at the end of the day, we all want to have application solutions for our customers, and then again, come back in a circular way into recycling technologies to solve at least one part of our problems we have at the moment, getting rid of CO2. Yeah, this is one of the things, and using plastic waste at the end of the day as a raw material. Yeah, and we are a company, and surely a company also wants to benefit and make value out of these approaches. And I'm talking about this balancing out, how we balance out these challenges, right? I now want to share my my screen. I hope it works. So so do you see it now?
Yes, I think. Yeah. Perfect. Yes. Wonderful.
Do you see my screen here?
It's all fine.
Yeah, thank you very much. So yeah, the title is Polyolefin Solutions for a Sustainable Future, how we approach it as a LyondellBasell. And yeah, it's always a if we go as a company out, we have always a forward-looking statements, that the statements is not based on historical facts, but are forward-looking statements. So the agenda, what I will talk about is 3 parts. So the first is who we are, to let you know what are our approaches, who we are, what we think, how we think in terms of sustainability. The second part is about LyondellBasell circular economy thinking. So one of the core messages we want to bring here, and also LyondellBasell solutions for a sustainable plastics future. Also coming up with some nice solutions, especially in the packaging area. So who we are? So we are a company which has commitments, values, competencies. So we want to be sustainability focused, and on this go for innovation. We want to perform better than ever, and we want to get an outside-in perspective. Means we don't want to go for a technology push. We want to get the market pull and the customer needs. We would like to map that, and we want to collaborate as we go towards a circular economy. We need to collaborate downstream of our processes, but also upstream. And at the end of the day, coming from a linear economy to a circular one, we have values. We want to champion, and we do champion people. We want to strive for excellence, and we shape the future. Our competencies are building partnership, deliver results, drive innovation, grow capabilities, and promote inclusion. So I will come then later on what that means. And we have 3 pillars of our strategy. We want to grow and upgrade the core, so it's the existing business. We want to build up a profitable and low carbon solutions business, circular business. So low carbon is very important with the CO2. And we want to step up our performance to have solutions for a better tomorrow. And we have been also mentioned in Bloomberg NEF's Circular Economy Company ranking as number 1. And based on this, under below, we always go zero, means we want to have no process safety, occupational safety incidents. This is always very important, that our people go to the company and go home again in a safe manner. So just to give a short overview, we have about 20,000 employees in the meanwhile. Half of it, if you look at Europe and United States, so 1-to-1, but we are also in Middle East. We are in Asia Pacific, Latin America. We are a big producer of polyethylene and polypropylene in Europe and are distributed over 21 countries with manufacturing sites and joint ventures. And we have 6,000 patents, and patents are very important. And this is your work which goes into these patents. It's scientific work, it's application work, it's innovation work. And we are the second largest producer of propylene oxide worldwide. And we also go for global gear days where we go out with our employees and collect waste, for example. Just an example here, we also go for food donations, as we see that we have a responsibility in our society. So we have very big ambitions. We want to end plastic waste and would like to achieve 2 million tons of recycled and renewable-based polymers produced and marketed end of 2030. We want to have zero plastic penny loss to the environment. So it's not only about CO2, but we also want to preserve the environment. Now going to the climate actions, we want to get net zero. I think you know that a lot of companies go for that for 2050. But we also want to reduce the Scope 1 and Scope 2 greenhouse gas emissions by 42% in our operations, and also 30% of our Scope 3 greenhouse gas emissions by 2030. And we want to reach 50% of our electricity, which we use. We want to get it from renewable sources. And many other, let's say, supporting targets for a thriving society. For example, also for the audience, perhaps important, we want to achieve gender parity in global senior leadership. And we are already in half of our target towards that target. So we have already reached 25%. We want to reach the 50%, which means then gender parity in senior leadership positions. We also want to increase the number of peoples from underrepresented groups, which is also very important. Why do I talk about these things? If we want to go into circularity and sustainability, we also need the power of many. And this means we need the power of the people in our company, which come from underrepresented groups, which come from all genders. I think it's the quality and performance of the people, which is very important, if we want to have success together. So highlights are, I talked before about that we want to reach our target of 50% in 2030, but we have already reached 100% of that target because we have purchased power purchase agreements already signed. So we have already secured that target. Why is it important for renewable electricity? If you talk about later on, if I talk about later on chemical recycling, you can imagine that an additional process like chemical recycling and also processes like purification will need energy, that's for sure. And at the same time, you don't only want to recycle plastics, but also do not want to create CO2. So this is, I think, very important. And we turn the risks into chances. We have already produced 123 kilotons, means 123,000 tons of recycled and renewable-based polymers in 2023. And then I will come back later on what it means really in numbers. How can I relate that to the overall production of polymers in LyondellBasell? It sounds like it is very much, it is already a big success. But if you talk about 10, 12 millions of tons of production in our assets, then 123 kilotons is just one part of it. We have trained a lot into diversity, equity, inclusion, a lot of training hours. So, and we are in the meanwhile a globally recognized leader in sustainability efforts. So also here we see, we looked into the market because at the end of the day, we also want to get business cases. We look into the market, we talk with a lot of brand owners, means like yeah, the daily things you as consumer, we as consumer buy. And then you see the brands on those consumer goods. These are brand owners. And in between us and the brand owners, we are converters from our plastics to applications, and they sell their applications to the brand owners, which, for example, use as a packaging, but not only, and then stamp the brand onto their packaging. And we see here that some of the brand owners, we have 10 of them, it's anonymously here, have talked to us, said, okay, they want to reach a certain target of 50% of the total packaging content should be recycled. Yeah, for example, this company, they have already projects recycled content on the way by 2025, like this portion. They have already a recycled content since 2021, and then in gray, you see a gap to the target. You see on the other side also other companies which have perhaps a lower target, but already have achieved it. So there is a big dynamic in the industry, a big dynamic in the market, and we want to get into this market. We get into this market with all of our solutions we have in the meanwhile in our portfolio. But getting to this target means that we also need raw materials. Yeah. So we see supply in raw materials in 2022 of 3 million tons. We expect that we will have a supply in the future in 2030 of 10 million tons. But the demand, we expect that it will be 50 million tons. And by this, we see between demand and the supply already a gap of 5 million tons of recycling feeds. Yeah. So also this is important. So we need to think about together where we can and how can we come to this target. How can we improve the recycling technologies? And before going into recycling, how can we improve the sorting technologies? Yeah. How can we improve the recycling scheme at our countries? Yeah. Some countries have in portions very good recycling schemes. For example, like milk bottle recycling in US, it's unbelievable. Milk bottles are recycled in US and are even then food approved, like the PET bottle in countries like in Europe. So we need new capacities to bridge this supply gap. And at the end of the day, we want to have healthy margins. But this seems that due to this gap, there will be margins where we can gain off. So what does it mean now for our circular economy thinking? What do we do? So first, and also you have seen the similar pictures by our colleague here before from BASF. This is a circular approach. What we have, we call it circular. It's a circular approach. At the beginning, or at the actual status, how it is, you have fossil raw materials which go into the plastic production, means goes into the refinery, then to the cracker, and then to the polymerization plant. Then you have production of the finished goods at our customers, because we produce polymers, which our customers convert. And customers means the converter, and then another converter, and then the brand owner. So it depends on the type of application we have. And then it is sold to us as consumers. Yeah? It is distributed and sold. And ideally, it is collected by household, by like the gelbe Sack in Germany, like PET bottles, like milk bottles. When you come back to a sorting, you can, and here starts the first pillar. You can mechanical recycling, or you can go into advanced recycling. And advanced recycling means either chemical recycling or dissolution technologies, or you can replace the fossil raw materials by renewable-based feedstocks and go into the same process like before. And if you go into the same process like before, you have a drop-in solution. Means that you are already food approved and that you can go into demanding applications which need food approval, but which sometimes cannot be done by mechanical recycling. So we think, and here it is what we have, we think that mechanical recycling and advanced recycling are complementary, to each other. And that was also one of the questions, I think, in the audience. How do you think about design for recycling for advanced recycling and how in mechanical recycling? I'm an engineer, and engineers tend always to say it depends. If you say it depends, it means that you already thought about in which application you want to go. And if you want to go, for example, in food approvals, like in Europe, we have the EFCE food approval, and the EFCE is very strict. If you compare it with the FDA food approval in US, this is just a kind of, let's say, if you are okay with that, you can take the risk. But in EFCE regulation means you have to deal with all the norms, and you have to cover all the norms, and then you are allowed, you get the certification, and then you are allowed to sell into food applications. If you go into advanced recycling and go through the whole process here, then by nature, you produce already very fresh polymers, which you can use in every kind of application. Nevertheless, there is a difference between mechanical recycling and advanced recycling. It's the energy usage. The energy in mechanical recycling is much lower than in advanced recycling. And also here you need to have some solutions for the energy which you use. Here in this in this slide, you see that we already have acquired companies which map all the needs you have if you want to go into a recycling business. So you need to source your waste, like we do already with joint ventures. You need to sort the waste, like also we do with joint ventures. Then you need to go either the other way, mechanical recycling. And here we also bought companies. So it's an inorganic growth, but if you want to be fast, you need to grow like that, like Rodepa. We also acquired other companies which are now part of our company, like Jelen, or even formerly a startup which is called APK for solvent recycling. Or you come up with advanced recycling, and here we have our own proprietary technology, which is called Moratech, so molecular recycling technology. And here we have a semi-industrial pilot plant running in Ferrara, which is in Italy, where also our researchers are. And we have a solution for the future. We expect the startup in 2026 with a 50 kiloton per year output of a plant in Wesseling in our integrated hub. After that, we will learn how we need to purify. There was a question of the audience in one of the other presentations. How much will it be? But if you compare 50 KTA, 50,000 tons, with our cracker output, and assume you have 1 million tons of an output of ethylene, and you can read it also in already non-confidential papers. If you have a yield of 1 to 3, you need already 3 million tons of naphtha, and compare that, please, to 50,000 tons. So we are at the beginning of a big journey. If you want to replace all of these raw materials coming from fossil-based with that amount of chemical recycling plastics or renewable offtakes. So this gives you an idea about the dimensions we are thinking of. And after that, you have produced your polymers. You go into the Circularity called production, which is then based on renewable offtakes. circular revive polymers, which is based on advanced recycling, and here circular and recover-based polymers, which are coming out of mechanical recycling. Just come to the MoReTec. MoReTec means molecular recycling technology. This is a differentiated technology. It has improved economics. Why? It is based on a catalytic reaction, which then produces substitutes. And the catalytic reaction means that it lowers the energy consumption, which is then good for the overall process. We have our own catalysts, which we also develop in our own company. So the whole process as such is an own propriety. And after having reduced with catalytic production or cracked the chains, we come out with pyrolysis oil and gas, and that is fed into the existing crackers we have. And the crackers, if you look into the literature, crack down those already pre-cracked molecules into C2, C3, which then can polymerize to polyethylene or polypropylene. And then, this is very important, identical properties to fossil-based polymers. This is why it is drop-in solution. And then you can use these recycled polymers in demanding applications such as healthcare and food packaging, which is very hardly to achieve with mechanical recycling. But mechanical recycling is complementary, as I said, for example, for industry applications. So here you see a pilot plant, just to show you a picture, not only words. It's the pilot plant in Ferrara, what we have. We do a lot of tests here. We learn a lot from these tests. We can show that it is possible. Based on this kind of pilot plant, we can now and will now build up a plant which will be 50,000 tons. And we already have commenced the construction. And the German Chancellor, perhaps you have read it in the news, Olaf Scholz attended the foundation some weeks ago for the stone laying. So it's not only a plan what to do, we already go into industrial scale. We walk the talk, we say. Yeah? We already go into materializing our plans. So our proprietary catalyst differentiates MoReTec relative to traditional pyrolysis processes, means traditional ones are like putting thermic energy into the process and let it crack then the polymers we have. But you can imagine that this kind of way is very energetic, yeah. So needs a lot of energy, I mean. And then, there will be a big shift in this energy usage. So we will decrease with our catalysts the energy usage by far. And we have at least here, not at least, but we have a deep expertise in our own company in catalyst technology. Especially in Ferrara. We have our own catalyst portfolio, and we are fit for the future with all our expert people. As I said, catalyst lowers the activation energy, you know that, and at the same time improves the yields of valuable pyrolysis oil and pyrolysis gas. Because if you put in 1 ton of plastic waste, you can imagine that will not fully convert to an oil and gas, which you can use. You will also produce waste, and you will also produce streams, which you again need to recycle. And a future development will be for sure to look again into that waste and convert it even much more into usable monomers for the cracker. So by this, you will understand that we need to go into a kind of purification technology as next step. MoReTec at the same time is supporting our net zero goals. Why? Because we don't only use mixed plastic waste. Yeah, this is one part of the medal, but you also need to use renewable energy for the new process if you want to reduce at the same time the CO2 footprint. And one of the questions before asked was, yeah, do you have LCAs for all these processes? Yes, we have LCAs for our polymers like polypropylene, like polyethylene, like polybutene and catalloy. But also we have LCAs for our renewable pillar, for our revive, and for our recovery pillar. So LCA is very important to judge on which way you want to go. Yeah, to judge on also, do you have a solution for the customer which is better than competitive materials? If I will come on later on that, we don't only want to use mixed plastics, but also our solutions which we give to the customers need to be lower in carbon footprint. But carbon footprint is not the only LCA parameter or output. It is one out of 60. So if you want to compare the advantages of one material to the other or one application to the other, you need to fully compare not only based on PCF, but also other parameters like water emissions, water usage, kind of other emissions you have in the process, and harm to the environment. So the LCA approach, I think, is the right one to compare holistically the advantages and disadvantages of certain solutions. So we want to impact the scope 1, the scope 2 and scope 3. Scope 1, we impact by this Moratec technology because we use pyrolysis gas as feedstock. Scope 2, because we it's by electrical heating of the process, we can use renewable electricity from solar, wind, or other sources. And scope 3, we displace here fossil-based feedstocks and divert plastic waste from incineration, landfills, or leakage into the environment. And we estimate that we will have 50% less carbon footprint than of fossil-based processes. Advanced recycling, so, is a critical part of the circular value chain. Then pyrolysis converts post-consumer plastic waste into valuable feedstock to produce new polymers. So we have a lot of capabilities, and limitations of traditional advanced recycling are, it's higher cost due to small scale, inability to reach commercial scale, lower energy efficiency, lower carbon efficiency, which we can scope with our catalytic process. Now I come to the third part of my presentation. It's about the solutions for a sustainable plastics future. So more concrete, what we are talking here about. And as you have seen, we have in our concept of Circulane 3 pillars like Circulane Recover, polymers made from plastics waste through a mechanical recycling process. Circulane Revive, we call it, polymers made by converting plastic waste into feedstock to produce new polymers using advanced molecular recycling process. And Circulane Renew, polymers waste made from renewable feedstocks such as cooking oil. And I want to emphasize here that we avoid competition to food, for example, by using cooked oil, which is a waste for other businesses. Like we do use naphtha as a base, as a waste coming out of the refinery process. So we are, at the end of the day, switching from one waste type of product to another one, cooking oil, without harming the food chain. So we have here different technologies. So in mechanical recycling, we use post-consumer plastic material. This is also very important, not post-industrial, like you see here in this picture, bottles, shampoo bottles, or other kind of bottles here, for example, from collecting streams. This requires a highly sorted and cleaned waste stream, and then we go into consumer packaging the goods again. Advanced recycling, this is hard to recycle plastic material, so not every material can be mechanically recycled, but you can recycle it by advanced recycling. You make pellets out of it, and then you feed an extruder, which is then feeding again the reactor, which is doing this chemical recycling. And you are more tolerant of mixed plastic waste by this, so you don't need to sort it very much down. But the very big advantage is, as I said, you can go into food packaging and healthcare applications because it is a drop-in solution. By the renewable bio-based source material, you have cooking oil. This requires feedstocks going into our process again directly. And here again, you can go into food packaging and healthcare applications as example. So I think because of the time, I will jump through some of the present slides, which are go more into detail about the three pillars I've talked about, and would like to show you at the end some kind of applications for monomaterial solutions and other kind of solutions. For example, this one, yeah, Circularity cover HD45U06 natural. Where does it go in? This product is a ready-made compound based on 60% of virgin HDPE. Virgin we call the polymer which goes out of our process, and then we take mechanically recycled 40% HDPE from industrial packaging. We use that, for example, for intermediate bulk containers and jerry can applications. And we have proven that this is suitable for UN-approved packaging, which means that by standard, these kind of packages need to be proven that they don't break, for example. Yeah, if you let them fall from a very high height, because if you have chemicals in such application, it needs to be tight and you need to test it. So this is application development. And it is comparable to a virgin HDPE in performance, processability, and odor. Yeah? Odor is a very, very important property of an application. People don't want to have odor in their applications. Yeah, this is very, very shortly understandable. We are according to the requirements of standards, ISO standards, and the HDPE, the Circularity cover natural contains at least 40% of recycled material that is fully based on post-consumer waste. Also very important. So this product is not intended for highly regulated applications such as food contact, portable water contact, medical and pharmaceutical applications, but for UN-approved packaging. So very nice example. So it's ready to use. This Circularity cover grade. You have a monolayer processing, single wall IBC is possible. Yeah, IBC means that packaging before. It's a 1 ton of volume which you can transport with that. It's a homogeneous compound. You have a strict protocol on density. You have an advanced product manufactured at scalable industrial compounding lines, uniform natural color appearance, and you see here the differences in the shape, a little bit in the shape and also in the color between the virgin and the natural one. So very, very well matching. So I also show you here the same application, yes, jerry cans, but this one is a virgin one. This one is reuse. So our target should also be reuse material. Yeah, but make it happen that or possible that it is reused. You can also take the Circularity cover grade. You can take also 100% PCR even, but then you are non-UN food, non-UN cosmetic. You can take Circularity renew-based material. Yeah, you can go into UN applications and food, or you can go into advanced recycling, and these are samples which were really produced and shown at conferences, for example. We are also, as LyondellBasell, working towards design for recycling. We are leading a working group for design for recycling in the CEN association, and we need to think about what needs to be the criteria of an application so it so that it can be recycled. So this is called design for recycling. And there will be, let's say, criteria, norms, which will call for this kind of recycling and design for it. And if you are not designed in future, you will get fees. So all of your applications downstream the chain will get the grade A, B, C, or D, and by time you will get fees. Yeah. So if you don't come to a compliance with the design for recycling criteria, like here, yeah, you even will not be able to pay fees. You even will not be able to sell it. So the thinking and the mindset in the society and politics is changing towards this mindset. LyondellBasell, as I said, is leading this polyolefin circular economy flat with work cream. It's a subgroup for polyethylene and polypropylene rigid packaging. There's another one for flexible packaging, where we also take part and give our input into these guidelines. This is another example, and this will be the last one. So we want to go from multi-material approach to monomaterial packaging. Means at the moment, a lot of packagings are with a lot of layers, and the layers consist of different materials. And you can see that this kind of materials, because it's so broad, it's not possible to recycle it. Not possible, at least with a kind of low energy process. And we have here given to the market solutions in our applications to replace multi-materials, but by monomaterials, but still you will have multi-layers, because the application as such needs to have some properties, like needs to prevent water vapor coming out of the atmosphere into the food, or into the, if it is some kind of fluids herein, or like oxygen, needs to be an oxygen barrier. So it's not an easy task, but doable. So you need to have a sealing, a barrier, the optics, it also needs to look nice. Needs to be a reverse printing also possible. It should be mechanical recyclable, and should be resistance, mechanical resistance, and it should be processable. And here is a kind of, this is more for conferences, where even more in this kind of business, the people know already what this kind of grades are. But I just wanted to show you here also how much engineered our solutions are. So if we as application development engineer these things, we are in contact with research and development people, we are in contact with marketing people, giving the outside-in perspective. We are in contact with asset people, plant people, so that they know what to produce and give them specifications into the hand. And we are in contact, and this is most important, with our customers, because they have their machines, which they, understandable, don't want to change. So we need to find applications which also fit to their processes. And by this, we have found here, for example, that kind of combination of products, which then have this high stiffness, high clarity, excellent stretchability, thermal resistance, dimension stability, and it is then 100% recyclable in a PE waste stream. And looks like this at the end of the day. Perhaps this is a PP example. The other one was a PE example, so polypropylene and polyethylene. And here you go from a mixture of PET, aluminium, and PP, just to a mixture of only PP. At the same time, you see also it gets a little bit more complicated, but the LCA as such, if you cover here aluminium, will be much more better than before. So thank you very much for your patience. I think we go for solutions for a better tomorrow in our company. Thank you very much.
Thank you very much for your very interesting presentation. Indeed, we do already have 3 questions, so I will start reading them out to you. The first one is from Dimitris Kolias, and he's asking, does the Moratec technology allow for reactor scale up or scale out due to heat management requirements?
Does the Moratec technology, can you repeat again the question?
Does it allow for reactor scale up or scale out due to heat management requirements?
The Moratec plant, so perhaps I talk about how it came to this kind of scale up. So the first ideas we made were with universities, yeah. So we searched for universities which are capable of doing tests in their labs and have experienced people in understanding polymerization, polymer reaction. So these were the first tests on lab scale. Out of this, we have understood what to do, and we have understood when it works, and then we have developed the catalysts. With that development of the catalysts and the understanding together with universities, we built up a pilot plant in a kilogram per hour scale. And this pilot plant I have shown you in the presentation. And out of this pilot plant and the tests we have done, we will now implement an industrial scale plant which will produce 50,000 tons, so in tons per hour scale. And we think that we will be able to go further, and the next plant will be to set up in Channelview, which is the other big site in our company in US, the next chemical recycling plant with more than 100,000 tons. Yeah. So as you say, yes, this is a very good question, because you need a lot of people to be able to do this. You need the people from R&D, you need the people from process engineering, you need people who are capable of doing projects, and you need also manufacturing people who are capable of starting up these kind of facilities. And then you need again go into this second iteration to be able to even more scale up.
Okay, thank you very much. So the next question is from Guido Caraglio. Thank you for your enlightening presentation. I would like to inquire whether LyondellBasell has a dedicated research and development branch or any particular interest in advancing recycling through hydrothermal processes. So it's about hydrothermal processes, if they are being investigated or assessed by LyondellBasell.
Perhaps I talk about first which kind of research facilities we have. So we have 3 of them, or even 4. So one is in Cincinnati, USA. So it's a combination of R&D with people like me from application development in one facility for whole US. Then we have 2 sites which are in Frankfurt and Ferrara. Frankfurt is more polyethylene based and Ferrara more polypropylene. But in both sites, we have people dealing with catalysts, dealing with processes, process research, and dealing also with product development. So by this, we think that we cover a lot of topics, but we have bought with APK also research people, yeah, bought in brackets, but we have onboarded them to be capable, who are capable of the solving technologies, right? So we have bought not only the asset, but also the technology. So sometimes we have not the technology on board, but we need to buy these kind of licenses, and then we can enlarge our portfolio. With hydrothermic, I think we made tests also with other kind of processes for pyrolysis or production, but you see that there's a huge energy gap in between, right? Nevertheless, always if you go into a new process, you need to think about heat integration. I think this is one of the most important things. Not only go straight through, but you need to think about heat integration. How can I reuse the produced heat in the process, again, in the same process?
Okay, yes. Thank you very much. So the next question is advanced by some explanation, maybe also for people from the audience who are not aware of that. So it will be a longer text that I'm reading out now from Fabian Rüth. At the EU legislation level concerning PPWR, there is the discussion that the fuel exempt use at mass balancing will only be allowed if you can prove that the input waste was not suitable for other recycling technologies with less energy consumption. There's already the proof that mixed PO from flexibles can be recycled mechanically, including multi-layer packaging. What can be the desired feedstock in the EU for MoReTec when you will not be allowed to have access on streams which actually can be recycled mechanically, like mixed PO from flexible packaging? Even if the quality of these recyclates is not as high as derived from rigids because of multi-layer and printing ink, but still is replacing virgin plastics without any doubt.
Yeah, indeed. So I've shown you before that we mechanically recycle. Yeah, we also have complementary to this the chemical recycling, but flexible packaging. For example, a mixture of LDPE based with a polyamide kind of structure. You can take this and dissolve it. Yeah. So this is the next, let's say, mosaic where you can use a technology like dissolving technologies and get into this, sort out by a dissolution technology the 2 types or 3 types of plastics, and then go with that output again into a mechanical recycling. It depends on where you want to end. You always need to think not only on the processes, but you need to think on the end application and where it goes to, and then not only the end application, but also the requirements of the end application. So you need to think in future holistically, and I can say some of our customers do that already. Yeah, I was 2 weeks ago with a customer. I do not name the customer, but I was astonished that the brand owner, and everybody of you know that brand owner, is knowing what in our processes is happening. Unbelievable. And this is the approach all of us need to do. We need to understand downstream and upstream.
Okay, yeah, thank you very much. We have one more question from the audience, from Mark Caballero. Thanks, Ugur, for the interesting talk. Based on your scope 1 impact, integrating pyrolysis into existing crackers, what would be the impact on the existing facilities of that new feedstock, both in terms of operation and equipment modifications if needed?
I think that our people we have in our site, and it is in Wesseling in Cologne area, are very excited because especially in Europe, you don't have unfortunately not so much the opportunity anymore dealing with new plants, with new assets, and not only new assets, but really based on new technologies. These people are excited, believe me that, and we are very proud on being part of the story. And it is really a challenge, but we will see. We'll also learn out of this. So I've shown you the dimensions of 50,000 tons of output. But if you talk about million of tons, what you need as a cracker input on the other side is just the beginning. And we will learn out of this, and we will need you. Other people, good people, universities, experienced people to understand what we need to do to be capable to increase that input, right? The topic is, and this you can take also home, it's not the story is always not about the main component in these kind of streams. It's always about the impurities. It's always about the, let's say, what is not working. What is working does not interest. What is not working is interesting. And I think this is challenging. And if someone is creative and curious, we are happy to work with you.
Thank you very much. So indeed, I think there are no more questions from the audience. We've stretched time already a bit. So thank you very much for your presentation and the discussion. And maybe now we do have some time for some final remarks or questions for all the participants and the speakers. So maybe you can switch on your cameras as well, the other speakers, and we can have a final.
Yeah, the program itself, it named it kind of a panel discussion, and we have now a little bit a reduced panel, but maybe that should be intended more for the generic thing, because for the in-depth discussion about the technologies, I think we had already good conversations. What is always puzzling me a little bit when I see these nice pictures, and I'm really enthusiastic about that, because a few years ago we were facing like bad reputation and blaming polymers and plastics in some way that they may be obsolete. And what was fascinating to me is that industry is apparently moving faster than academia even. So what you have seen with Moratec, what you have seen with the other parties is that on a very quick time basis, and this is what you can be very proud of, has been moved. When we were discussing, we had a few discussion rounds about circular technologies and so on, and when we talked to other people, from other technologies like paper, like battery recycling, not lithium-ionic batteries, but the classical car batteries, paper, glass, it was always the recommendation, get your backflow under control. And I think this is something you already addressed also in some way. We had it also in some questions, so that you addressed it in terms of sorting, but I'm interested also what other efforts are. So it would not make sense mixing everything if you have customers that buy, for example, foils, and if you can recover them selectively, this would greatly help. So can you talk a little bit about the efforts in this direction? So this is we have unfortunately only one industry representative here, so it may be more direct to Ugur. For the others, it's a little bit. Universities are not that under control of backflow, but maybe you can give an idea how you look at that.
Perhaps I have understood. I hope I understood the question right. We are indeed in talk with a lot of customers, and this means because our segments go into very diverse directions like medical, pharma, automotive, packaging, piping. You can look into your, let's say, private environment where plastics go. I like more the German word of Kunststoffe, yeah, because it's a little bit saying more than plastics. Because it talks about the properties also of the plastics, and you go into a lot of applications like automotive, where we also are, like I think also BASF, Dow, and also other companies are, and also here the landscape is changing. Not only because it goes into electrical vehicles, but also if you look into a car, there are a lot of components which consist of plastics, and also there is a directive coming up where the automotive producers need to deal with, the end of life directive. Mm-hmm. And this is really a big thing, because end of life directive means that I don't know when it comes. It's I think 2030 or 31, but at that time the cars already need to be recyclable in a certain manner. But if you think in the cycling time for these kind of designing a new car, you already need to design now the cars for the future, which goes onto the market in 2030 or 31. So there is not much time anymore.
Yeah.
Perhaps
so this is what I mean. And the intention, in my perspective, the intention must be that you have very diverse streams, because of it is it is material by process, so properties, material properties by process. And as best you can keep it separate in different flows, as best the quality of the local cycle, not locally in terms of area, but in terms of application should work. And this would mean that you have to completely change in thinking about material flows. At the moment, everything seems to be coming back, and you're putting a lot of energy in sorting it back out. I have seen fascinating machines that can separate in enormous speed different fragments of plastics in the right manner. But that means that you put in efforts that you could have saved before. And the question is about, apparently I understand that there are intentions to keep these slopes separate and to gain profit from that.
Yes, indeed. I mean, we need to go with design for recycling kind of way. And I think by time, this is my personal belief, by time, if the products are designed for recycle, also it will have an impact onto the recycling streams coming back, and they will be by time more purer and purer. And by this, the whole sorting process and also the volume of the feedstocks coming back will increase, and the quality will increase. But I think that's a matter of time.
Yeah, I think that's the direction to go. So are there other contributions, either from the panel or from the audience or whatsoever?
Now, you mentioned a few moments ago, the difficulty of using raw materials which are coming from biological processes. And this is really a problem because, as you know, fermentation is more than 90% water and only a small amount of biological material. And this means enormous reactors to produce a very small amount of biological. We still have to remember that more than 90% of all the monomers we use are coming from petrochemicals. And this cannot be the future. The future has to be really monomers which are coming from nature. And therefore, where we have to find monomers is in the wood of the trees and in the algae and in sinks which are capturing CO2 and converting CO2 in organic matter. This is the future. To find monomers derived from wood, we are doing some on that direction by making simultaneous depolymerization of lignin and celluloses at low temperature to allow for recovering of the sugars. But there's still a lot of work to be done to recover monomers, to take monomers from the nature.
I think that was more a statement than a question.
Yeah, but it is an interesting point. We can debate about that. This is indeed the case, but you may correct me with the numbers because you're closer to. But I think we are using like 400 million tons per year of ethylene. Is that somehow correct?
You mean the overall demand in the world?
Overall demand, yeah, 400 million tons of ethylene per year. And what I have in mind is that you can make an ethylene bio-based, and it is, I think, the largest monomer. And if you take any alcohol from the bio-based alcohol, converting it into, then we are around like 36 million tons. And I think this is what he is addressing. So we have a big gap, and we don't have a single stream. And my personal vision in this direction is that we will have a multifold stream. So we get much more diverse in terms of resources. So we heard about the about the wood-based stuff. I have heard about bio-based stuff, so biotechnology-based built monomers, and we have this recycling. But I'm pretty much convinced that we will have different feedstocks, not these single-line feedstocks, but more different feedstocks where we have to live on. And for the people in manufacturing and polymerization, This will be a very great challenge to adapt the individual process in a way to cope with this diversity. So that would be, I think, the major challenge. And at the end of the day, we have seen all these pictures with these cycles. The exit stream should be minimized and the entry stream should be, so we have to minimize the exit stream. We have to keep in mind as much as possible, because the entry stream from renewable basis is in numbers much smaller, and then we may cope with the problem. Yeah. More comments? So the other thing what is puzzling me is always, we are now very much in the forefront in the US and here in Europe. And part of the problem is not generated here. So it does not help if we hunt the very last pellet here around in Western Europe or whatsoever, when the origin from pollution of plastics and so is somewhere else. On the other hand, and this is something I think we have to understand, our industry has to understand, but we as a society have to understand that we share this development. So what would be interesting for me is to hear about the perspective, how companies think about that. I learned in terms of safety from the aircraft industry that they understood that they could turn down numbers of events, so fatal events, significantly, but the consequence was they are too rare to learn on their own. So they have to share to improve further, but they do because they understand that an impact is impacting the whole community in a negative way. And if you transfer this picture, it is a little bit the same. It does not help if we solve problems here, if we do not share and help to solve the problems at other places. So what would be the perspective of companies looking at this, sharing technology, exporting, licensing? So you have been pretty honest about you would like to earn money, you have to survive. But on the other hand, we have to solve the problem. Can you share a little bit about the perspective in this respect?
LyondellBasell is a company which licenses all the processes. We do that in our hostile technology. We do it in other kind of technologies. We sell catalysts. We develop and perform on catalysts, sell them. We have joint ventures, and even the Morotech technology will be for sure licensed also in the future. If we can give confidence that it works, and it works, we build up the scale-up plans. We will also, for certain companies, also sell it, right? I can imagine that because it is in the interest of companies, and this is like how it works, that they want to gain profit, right, out of that what they have invented. It cannot be just a proprietary technology and not selling also the licenses to increase let's say the impact on the environment on the whole world. But as you said before, even here again, Europe has kind of invented in that example again a new technology, and this is perhaps also the let's say the core of Europe. Perhaps we cannot solve the CO2 as such, but we can give a kind of role model. We can invent processes and technologies and then also make a business out of that. So that is possible. Why not? I think this is just a global planet here where we live together, and we need to solve that topic of CO2 together. This is what I can say.
Yeah. Thank you very much, sir.
Thank you.
Any more contributions?
I need to unfortunately step out because my computer will automatically restart in 1 minute.
Good. if this happens, thank you very much to you. And it would have been in any case the final words. So thank you very much for all the contributors. Thank you very much to all the participants. It was a very nice afternoon, a very late evening in some areas, I would like to close then this session. I look to Martin if there are some final words from the EFCE, and otherwise I would wish everybody a very nice afternoon, night, and a good community and a good reconvention for the next meeting. So Martin, do we have any comments, any words from the EFCE?
So thank you for these nice words. So it was a very nice webinar. As usual in this series, I think that the spotlight talks are very successful. You can see the number of participants. It was very high during all the webinar. And don't forget that you can watch this video, the record of the webinar by videos on the EFCE YouTube channel. It will be available very soon. Thank you for all the participants and all the speakers, and also Kristina and Markus. Bye-bye.
Thank you.
Thank you.
Bye.
Have a good night.
Bye-bye.
Bye-bye.
Good night.